Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Alright, step on inside, and we are going to be reviewing some things that we've been doing based on exponential and radical properties. This is actually spanning over a month ago, I'd say, when we've been doing this. Just some more of it, more of the same stuff. Unit review for some of my students as they need to brush up on it coming out of the semester, out of the spring, fall semester into the spring. And then rational functions. Now we've graphed rational functions in the past, the basic variety. We've even done that in a bigger review. And then my most recent video was graphing more complicated rational functions. So this one, as a practice exam of sorts for my students, is something where I'm going to assume that they've heard it before. Something where I'll do the problems, but I'm not doing a full reteaching. I will be explaining as if it was an inner dialogue. Something I sometimes ask my students to say, have an inner dialogue. Talk about the problem as you would hear me talk about the problem. And I think that that's something that can always help you. Yes, there are steps involved, but they are natural. Or, you know, they fall in nature with what it is that you're trying to do in the problem in both forms here. So I'm going to jump straight into it, guys. Here we go. We got 6 problems. Here's the preview. You have PDF down below, by the way. I always say that, and half the time I don't do it. 6 problems simplifying rational exponents and or radicals within these things right here. And then there are some things involving not yet graphing them, but given functions, trying to detail some of the information, trying to write an equation based off information. That's new for my kiddos. And then graphing them here. And then, oh, I have a surprise one where it's already factored for you, in factored form, developing a sign chart for the for somebody. So I'm just going to go ahead and jump straight into it, guys. Simplify each expression completely, numbers 1 through 6. So starting with number 1, I do have a negative exponent, and it is a fraction. Now, I'm going to start with that negative portion and just talking about it here. Well, actually, you know what? Let's do 2 and 1. Yeah, let's do 1 and 1. I got enough space. Let's start by turning it positive by flipping this fraction on its head and turning it into 5y to the 4th divided by 4x squared. And that's what's happening here, and this is raised to the positive 1/2 power. Now, raising to the 1/2 power does mean taking the square root, right? Raising this to the first power and then the second root of that. So that does mean take the square root of these things. Technically, we're taking the square root of everything. I'll just split it into top and bottom, but we're taking the square root of 5y to the 4th divided by the square root of 4x squared, which again does mean you are taking the square root of everything in here. You are taking the square root of 5. You are taking the square root of y to the 4th. That's a 4. You are taking the square root of 4, and you are taking the square root of x squared. Now, I don't happen to be writing that 2 that would represent a second root right here. I'm not writing it, but you will have to remember that that does mean that you are then dividing your exponents by 2. That's clearly what the rational exponent was telling you, and some people would probably prefer to see it that way. When you multiply 4 by 1/2, you're dividing by 2. 2 times 1/2 dividing by 2. I put it in square root form. I'm going to have to do that with numbers, so here it is. The square root of y to the 4th, 4 divided by 2 is 2, so that becomes y squared. So on the top, I get y squared. And there's still the square root of 5. See, I can't take the square root of 5, so I'm going to leave it like that. We'll see that a couple times in here, I think. The square root of 4 is 2, and I'm going to turn that into that down below. And the square root of x squared is just x, as, you know, there's nothing. 2 divided by 2 is 1, and that's what we keep it as. And this is as simplified as we can get. The y's and x's can't interact with one another in any sort of way. Neither the root 5 nor the 2 can. So we're just going to leave it like that, and that is your final answer. Yes, sometimes answers do have radicals with them. Okay, number 2. 2x squared is all being raised to the 4th power, and then we're taking the square root of 27x to the 27th. So raising to the 4th power does mean you are raising the 2 to the 4th power as well. To put it bluntly, it is 2 to the 4th times x squared to the 4th. Now, in doing the square root of 27, remember, this is going to be a split. I'm going to be doing square root of 27 separately from the square root of x to the 27th. When I'm doing the square root of 27, it's not a perfect square, but there is a perfect square factor that exists inside of it. And just like x to the 27th, we're not taking the square root of this 27, we're dividing it by 2. But it's also not a x to the 27th isn't a perfect square because 27 doesn't divide by 2 evenly. So there's something we're going to have to do there. 2 to the 4th is 16. X squared to the 4th is not x to the 16th, it is x to the 8th because we do 2 times 4. So that's going to be x to the 8th power. Now we're multiplying this by, see, root 27, I can turn into the square root of 9 times the square root of 3. And I do this because I'm finding a perfect square factor that I can take the square root of, which is 9. 3 I can't take the square root of, so I'm not going to. When you do this 27 divided by 2, you think of it kind of like long division, and the thing that you can pull out is the quotient. The thing that is inside is the remainder, the thing that remains. 2 goes into 27 13 times. That becomes x to the 13th there. And the thing inside the square root, what remains is just an x to the first power. See, we took the square root of, again, that's a 2. We took the square root of x to the 27th. 13 times 2 is 26, plus the 1 remainder stays inside there. So x to the 13th root x. Sometimes the way that people split it up is they turn it into square root of x to the 26th times the square root of x, which is still the square root of x to the 27th. But dividing this by 2 gets you that x to the 13th right there. So hopefully that's helpful as well. One thing I want to mention before I keep moving forward, somebody might confuse this with a fourth root, like instead of like treating this separately here and then right here thinking fourth root of that. If they do have a fourth root, it would be more above the radical. Look right here. See that 4? It would be more above the radical right there compared to just to the left of it. So just to not confuse you with what's what. I could have put a dot symbol to indicate multiplication, but I did not. Okay, the square root of 9 is 3, right? This is 3. So 16 can multiply with that square root of 9, with 3, and that gives you 48. So I get 48 right there. X to the 8th can multiply with x to the 13th, and there the exponents add, and you get x to the 21st power. Now the root 3 stays inside the radical, and the root x stays inside the radical. They will remain inside a radical together to get root 3x, and that is your final result. For my students concerned about some of these problems, I mean, this is not way overzealous, but the idea is that the practice exam problems will be harder than the actual exam problems. That's just the nature of them. All right, number 3, I have this quantity raised to the 1/2 power and this quantity raised to the negative 1/3 power. I'm definitely going to address that negative 1/3 power given that negative, and I'm going to end up moving it down into fraction. It'll become 64x cubed y to the 9th to the positive 1/3 power. So let's just go ahead and write that. And right now I might already turn this 1/2 into a square root there. So square root of 4x to the 10th y squared. And hey, maybe it's the time. This is going to turn to the positive 1/3 power in the denominator, right? So that also means cube root. So cube root of 64x cubed y to the 9th. So it turned into a positive 1/3, and a positive 1/3 power is a cube root. So square root on top, cube root on bottom. Let's start taking roots. The square root of 4 is 2. The square root of x to the 10th is x to the 5th. And the square root of y squared is y. The cube root of 64 is 4. The cube root of x cubed is x, and the cube root of y to the 9th is y cubed. Again, we are dividing by those numbers there. Square root is the second root. Keep that in mind. Now we can simplify a little further here, right? 2/4 can reduce to 1/2. So a 2 on bottom, a 1 on top, but I'm going to have something else here. Generally, we don't put a 1 if there's, so I'll erase it in a second. X to the 5th over x, I can remove the x down here, remove an x up top, and you have x to the 4th. Hold on, I lost my color. X to the 4th, like that. That means that that 1 is effectively gone. 1x to the 4th is also x to the 4th. You can have it either way. And then the y, I can remove the y from the top and 1y from the bottom, and I'm left with y squared on the bottom. So as far as simplifying goes, of course, reducing fractions, among other things, that would be your result right there, x to the 4th over 2y squared. All right, number 4, kind of strange dealio with a bunch of fractions here. Now, I can't interact anything here and here until I deal with the square root, right? It's order of operations. Square roots identify with parentheses because it's a grouping, as well as square brackets would and anything like that. So, or it's like an exponent. Let me put it that way. Let me do this right now because this is going to be ever too important for us. I'm going to rewrite this so that instead on top I'm raising to the 1/2 power. Now you saw in previous problems where I was turning this into a square root, and there are two reasons to that. Number one, they were easier numbers to divide by 2. what's 11 halves divided by 2? That's not something we really mentioned. Number 2, we had numbers to deal with as well. So there are reasons why you might turn something to a square root versus not, or versus a rational exponent. But in this case, I think I'm more comfortable with doing this because I want to multiply these by that 1/2. And I'm going to spell this one out a little more here over time. So the thing I was trying to mention before is order of operations. Forget grouping and such. This is an exponent, right? It still goes before division. Exponents go before division. Now that 1/2 there, we're basically going to be raising this to the 1/2 power and this to the 1/2 power, which means the 1/2 multiplies by the 11 halves and by the -1. So right here, x to the 11 halves to the 1/2 is x to the 11 halves times 1/2. And 11 times 1 is 11, 2 times 2 is 4, so you get x to the 11 fourths. And then y, -1 times 1/2 is -1/2. So this is y to the, -1/2 power. On bottom, I have x to the 3/4 times y. Oh, I'm sorry, that should be a y right here. Times y to the 3/2. Okay, I wouldn't convert to rational or to radicals right now. I would definitely look at subtraction anytime, I did the whole removal thing here. The removing idea is a subtraction basis. When I remove the x here, I've subtracted 1 from the bottom. I did 5 minus 1 to get 4. And, like that. So right here, as you're working this is x to the 11/4 minus 3/4 power times y to the, do I want to, you know what, I'm going to deal with the y in the denominator. I didn't even see that was negative. Let's take this here and bring it to the denominator, so it's y to the positive 1/2 power. So now when I'm doing this here, I'm subtracting up top, and I'm really dividing down below. So this is all divided by y to the 3/2 plus 1/2 power, and they're in the denominator. They're in the denominator. That's why we're doing it down there. And why is this in the numerator? Because I'm dividing. I'm taking something divided by something else, and that leads to subtracting of exponents. It's just a numerator result. These are just denominator values right now. So okay, 11/4 minus 3/4 is 8/4. 3/2 minus 3/2 plus 1/2 is 4/2. So what are the 4/2? So 8 over 4 is 2. You get x squared. And 4 over 2 is 2. Excuse me, 8 over, did I say that right? Yes. And you get x squared over y squared there. Number 5, let's find a color I haven't used. Number 5, the 4th root of 81 x to the 5th y to the squared z to the 8th divided by 36, the square root of 36 x to the 18th z to the 20th. Taking a 4th root of 81 is 3, and then taking the 4th root of these things here, we would divide them by 4. Now 5 can't divide evenly into 4. 4 goes into 5 once, so I can pull out an x from there. Now what will remain inside here is still a 4th root of x. There is still an x to the first that remains. That's the remainder. 5 divided by 4 is 1, remainder 1. The 4th root of y squared, I can't pull any of those out. 4 can't go into 2 at all. So the y squared still remains inside of that radical with those. And then the z to the 8th, the 8 divided by 4 is 2. You get z squared. Ultimately, that's going to kind of hang out over here with the others. I just did this in order. And then divided by down here, we have the square root of 36 is 6. The square root of x to the 18th, 18 divided by 2 is 9, so we get x to the 9th here. And then the square root of z to the 20th, 20 divided by 2 is 10, so you get z to the 10th. So, okay, that's just an x to the first, keep in mind. That 4th root has to do with that part there. So as far as reduction goes, 3/6 is, once again, another 1/2 here, and it looks like I don't have to write the 1 on top because other things are going to be up here still. But not the x, because I removed that x from there. I removed 1x from here. I'm left with 8. And not the z's. I removed both the z's from up here. I removed 2 z's from down here. I'm left with 8 z's down here. So the only thing that remains up top is this 4th root thing. It's 1 times the 4th root of x, y squared. And on bottom, I have 2x to the 8th, z to the 8th. I'll take that. 2x to the 8th, z to the 8th. Now I can't work these. There are ways you could try and do some more subtraction stuff and all that, but you just be left with negative exponents or radicals in the denominator. We're good there. If there's nothing you could pull out from this part here and there aren't multiple radicals involved, as long as I took care of the x's that are all on the outside and the z's on the outside and stuff, I'm good. That's as simplified as we're really going to get. All right, lastly, number 6. Lighter green. Number 6 here. First of all, y to the 0 is 1, so I'm just going to already just cross it. It's gone. It's 1, and any of that times 1 is anything. And this negative exponent right here, I really like to work on simplifying things inside of the quantity before I really deal with what's outside, unless it's something like a negative and I have to flip it, which is exactly what we're going to do. So on top of this is only an 8 inside of this quantity, as the x to the negative 6 move down here, become x to the 6th. And I have z to the 9th right here, and we're raising this still to the 2/3 power. Y to the 0 was 1. It's gone. Over here, I can turn this to the first power, positive first power, by flipping this into x to the 8th z divided by 4, like that. To the first power, just means just this thing right here. So once I get this thing out of its parentheses and it's, radical and stuff like that, I'm going to convert it to a radical. All this kind of stuff here that I'm really taking care of. Actually, here, I'm going to do this first. I'm going to say this is 8 to the 2/3. So you're raising everything here to the 2/3 power. 8 to the 2/3 power, x to the 6th to the 2/3 power, and z to the 9th to the 2/3 power. As long as that 2 is involved, I think taking 2/3 of a number is easier here, and I can convert this to its radical form. This is once again times x to the 8th z over 4. Now, 8 to the 2/3 power, that one I will definitely convert for us here. That is the cube root of 8 squared. Oh, running out of room on this problem. Times x to the 8th times z. On bottom, x to the 6th to 2/3, we do 6 times 2/3. 6 times 2 is 12. 12 divided by 3 is 4. 2/3 of 6 is 4. You get x to the 4th power. Oh, by the way, there's a 4. Let me write the 4 kind of first here. That 4 right here. So we got a 4 there. Times x to the 4th times, and 2/3 of 9 is what you're doing there. 9 times 2 divided by 3 is 6. So you get z to the 6th power. So all that's left here is kind of some reduction. We still got to simplify the cube root of 8 squared. Again, running out of room, my bad. All right, the cube root of 8 is 2, and 2 squared is 4. So you're left with 4 on top, 4 on bottom. The x to the 8th, x to the 8th over x to the 4th. Remove all 4 from bottom, remove 4 from top, you're left with 4. Remove the one z from the top, remove a z from the bottom, you're left with 5 on bottom. So the 4 over 4, by the way, is going to become 1 as well. Those are going to go away. All that you're left with is x to the 4th on top, and it looks like z to the 5th on bottom. Honestly, that is the end result. X to the 4th over z to the 5th. Nothing else involved in it. That is definitely much further simplified than the stuff that we had before, right? That surely cleaned up. Whereas these other ones are like, did we really clean this thing up? Is it much better than it was before? I don't really know. All right, so there's that. All right, so that's the exponential property stuff, playing with that again. It's, being a little creative and just trusting the process and boxing it when you feel you're out of parentheses and radicals and stuff like that. All right, we're getting some of the rational stuff. Prior to graphing, just listing out some details, making sure that you're doing, not necessarily in this order do we do them. And I don't know if I really gave you a lot of room to do these things here, but you are going to try and find horizontal asymptotes, vertical asymptotes, intercepts in any existing holes. And it starts really through the factoring process here. I can factor a 2 out of the top and I get x squared minus 4. I might have to erase that and factor that further in a second. This on top can factor to x plus 3 times x minus 2. Now that I'm, working with really, higher level students with this, I'm not explaining why that is. That's something you really, need to know now. The x squared minus 4, again, for room's sake, that's a difference of 2 squares. That is x plus 2 times x minus 2. So that's the factored form of this f of x thing right here. Now, some things to work with. I'm actually going to find the hole or holes or whatever first. The x minus 2's cancel, and really that's where you find your holes, where you have canceled factors, such as the x minus 2's. where you get 0 over 0 is where x equals 2. So the whole exists at 2 comma something. We got to figure out that something. What I'm going to do is substitute, and mentally so, I'm going to substitute 2 in for x into this portion right here, the simplified portion that after you've canceled it out, where you don't get 0 over 0 anymore. So what's the y value of the whole of the non-defined x value? You do 2 times 2 plus 2 is 4. So you get 8 over 2 plus 3 is 5. So you get 8 fifths. So 2 comma 8 fifths is the location of that whole. And just, by the way, just as a heads up, sometimes you won't have x-intercepts, y-intercepts, holes, things like that. Sometimes things will be missing. So just be ready to put none if something's missing. We don't always have holes. Y-intercept. Y-intercept, oh wait, what order should I go? Let's go to vertical asymptote next. Vertical asymptote here is where you divide by 0 for anything that remains in the simplified version, because that would give you non-zero divided by 0. That's how vertical asymptotes work. Students really still haven't asked as to why vertical asymptotes appear in those, whereas holes appear in the other ones. We'd have to really play with limits, plugging in numbers really close to -3 and to +2, and kind of getting the idea of what's happening with that. Anyway, the vertical asymptote is at x equals -3. Now, to remind you, we're writing x equals -3 because this is the equation of the vertical line in a graph. This is the equation of the vertical line that we're describing. X can't equal -3. It's not allowed. It's a domain restriction. X equals -3 is the equation of the vertical line. That's what they're asking us to write. Let's go horizontal. Let's go horizontal asymptote next. As there is a tie in the leading degrees, the degrees of the leading terms of the top and bottom of this rational function, you are left with dividing 2 by 1. You could do long division on this. I don't think, because we're graphing, using long division is going to be important, but the quotient in essence will be a 2. 2 divided by 1 is 2. The horizontal asymptote is y equals 2. When there's a tie, you divide the leading coefficients, and you get y equals 2, which is, again, the equation of this line, a horizontal line that goes through. X-intercept, we take a look at when we get 0 in the numerator, because that's when we divide 0 by something to get 0 for y. When does 2 times x plus 2 equals 0? Well, that's when x equals -2, right there. So -2 comma 0, I like to write it as an ordered pairs. That's something that we're plotting. And the y-intercept, we set x equal to 0. And I sure love to do it in this equation, the original raw one, because plug in 0 into any of these x's here, by, and you're left with -8 over -6, which is +3 over 4 over 3. Positive 4 over 3. So the y-intercept is 0 comma 4/3, like that. All right, some good information there. We're all good. Same for numbers 8 and 9. Same kind of process. Last time I did it, I did 1, then 2, then 3, then 4, then 5. I don't think there's really there isn't a necessary order, but you're not getting x-intercepts unless you factor. You're not getting your holes. You really probably want to do holes first, because if you decided to keep the x minus 2's right here, and you said, oh yeah, x equals 2 is also an x-intercept, and x equals 2 is a vertical asymptote. It's not. It's a hole. There's no defined value there, and it's not a vertical line. It's just a jump in continuity. So you really want to do the hole first, and while you're in line with that, look at the domain restriction on the vertical asymptote. While you're there, just talk about the horizontal asymptote, because you got to draw those. I don't know. And then the intercepts, x-intercept is from what you've already factored. Y-intercept, we go back to the beginning. There it is. If we're talking about oblique asymptotes, we'd have to do long division on this, and maybe you'd wait a little longer. Okay, let's move forward. Number 8, g of x equals. Now I see a common factor of x on top, and you get x squared minus 16. And I see a common factor of x on bottom, and you get x squared plus 16. Now, x squared minus 16 is a difference of 2 squares. I'm going to go ahead and erase that and turn it into x plus 4 times x minus 4. Wait a second. Well, this is going to become x plus 4 times x minus 4. The bottom, however, is a sum of 2 squares, and not named so as to hint to you that it's factorable, because that's not further factorable. X squared plus 16 doesn't turn into, some x plus 4 times. Sum of two squares isn't a thing. Sum of two cubes is a thing, but sum of two squares, it's not for real numbers. That's not how it works. We do have an x over x right here that can cancel, and that does lead to one of our holes. So we do, once again, have a hole for this one. That hole is at x equals 0. Some of my students are still having trouble with that sometimes, recognizing that the 0 for that is if you plug in 0 in for x, you'll get 0 here, because 0 times anything is 0. So let's now plug in 0, and this is pretty easy. Let's now plug in 0 into this part as if the x over x isn't there. And we get 4 times negative 4 divided by 16. So negative 16 divided by positive 16, that is a negative 1. So there's a hole at 0, negative 1. Important to talk about the idea that that means there's not going to be a y-intercept, because if we have a hole right here, whatever the graph does, I don't care what the graph does, whatever the graph does, it's jumping that point. There's clearly no y-intercept. And just to speak on the matter now, substitute 0 for x into here. You get 0 over 0. That's the indeterminate. So there's no y-intercept. All right, let's go to the vertical asymptote stuff, though. Now, vertical asymptote is setting all of the remaining denominator factors equal to 0. So when does x squared plus 16 equal 0? And this is a bit of a trick question, because to solve this thing, we would tend to solve by factoring, but this is not factorable, so you'd probably solve using square roots. Subtract 16 over, x squared is negative 16, and then take the square root of both sides. That's not negative 4. That's not negative 4. You can't take the square root of, well, you can for imaginary numbers, but there is no real solution to this thing. There is no square root of negative. Think about it. You can't plug something into x, square it, and then add 16 to get 0. When you square it, it's going to turn positive. There is no other x value that works here. There is no vertical asymptote for this, which is a little different for rational functions. You haven't seen it before, and you're like, all the rational functions you guys have seen are like this, and you have a curve, and like, what's this one going to look like if there's no vertical asymptote? I couldn't tell you off the top of my head, but they tend to have some, like, there's a horizontal. Yeah, there's a horizontal one. Whatever the horizontal one is, it tends to do some sort of like humpty hump like that and kind of work like that. It's not the true appearance of a rational, also not why you're not graphing it. But yeah, no vertical asymptote there. Horizontal asymptote, there is one. It's, once again, there's a tie, x cubed and x cubed. So you divide 1 by 1 and you get 1. There's a horizontal asymptote at y equals 1. The x-intercept, we set y equal to 0. So you're looking at, when does this numerator, x plus 4 times x minus 4 equals 0. And of course, that would be x equals negative 4 and x equals positive 4. So there's an x-intercept at negative 4, 0 and positive 4, 0. If I had to put money on this problem, on graphing it, if we're talking about a asymptote of, I don't even know where to draw the graph. If we're talking about an asymptote of y equals 1 and x-intercepts at negative 4, 0 and positive 4, 0, and I guess just given the appearance of this thing, it's probably symmetric. It probably does this. Oh, what's the y-intercept? Oh, there's a hole. A hole at 0, negative 1. It probably does this. If I were to put money on the graph, that's what it would do. And it would approach the asymptote there. I don't know. But given our points, that seems to make sense. And that's kind of what they would do, given no vertical asymptotes. All right, number 9, factoring here. 4 is a common factor on top, so you're left with 4 times x minus 2. And on bottom, 4, no, 4 is not a common. Oh, we have a nice little case of factoring old school methods here. I have 4, which can either be 4x squared, which is either 4x times 1x or 2x times 2x. And I'll tell you what, it's going to have to be 2x times 2x because I got an even linear coefficient with only odd factors here. It's going to have to be them 2x's. And it's either plus 3 minus 1 or minus 3 plus 1. Looks like it's going to have to be minus 3 to make this thing negative. It doesn't matter where we put them because they're both multiplied by 2. Negative 6 plus 2 is negative 4. And there it is. So there's the factorization. Now, nothing cancels here. So in this case, there actually are not any holes here. Nothing canceled. Vertical asymptotes, however, we set these equal to 0. When does 2x plus 1 equal 0? And when does 2x minus 3 equal 0? Right? That's the idea. Subtract 1 from both sides. Divide both sides by 2. X is negative 1/2. That is one of your vertical asymptotes. Add 3 to both sides here and divide both sides by 2. You get x equals 3/2. hey, it's the first time we've seen fractions of those because it's the first time we factored ones that are not of the basic level that we've seen for quite a while there. Horizontal asymptote, your numerator's degree is smaller than your denominator's degree. That means that your denominator is going to get massively large as x, n behavior-wise, goes toward positive or negative infinity. That means you're getting really close to 0. This is a y equals 0 horizontal asymptote, as the numerator degree is smaller than the denominator degree. X-intercepts, we see when this equals 0 up here in the numerator, that's when x equals 2, so there's 2 comma 0. Y-intercept, we set x equal to 0 in this equation here. Bye. You get negative 8 over negative 3, which is positive 8/3, or 2 2/3. And that's the y-intercept there. All right, that's the information for numbers 7, 8, and 9. Moving on forward to number 10. New kind of problem as well here. In factored form, find an equation of f of x with the following properties. Vertical asymptotes, whole, etc., etc. Now, the interesting thing about this here is I don't really know what to say about that whole for now when it comes to the y value. I think everything's going to have to luck itself out in saying that as long as everything else falls in the way that we expect it to, that the 18/5 will just happen the way it does. And I think we got to kind of say the same thing for the y-intercept, given that we got to plug in a 0 for x and see if that y-intercept just naturally comes up. And if it doesn't, we're going to have to make some modifications to it. But let's start with, the idea of the vertical asymptotes. Horizontal asymptotes kind of involved here, and the x-intercepts. So the vertical asymptotes are, once again, where in your denominator, where you're dividing by 0. And only existing as factors in the denominator. In the denominator, we would have an x plus 3 and an x minus 1. That would leave you with these vertical asymptotes. Now, one thing I do need to mention about the whole, because the whole is kind of a portion of this. Wholes happen where you have canceled factors on top and bottom. If 2 represents the x where you have a whole, that means you have an x minus 2 both on top and bottom. That's what gives the whole. Now, I'm not going to multiply all these out. The final result's going to be in factored form, so please don't write these and then cancel them. Leave it just in factored form like this. If I wanted to distribute it, and I could, I would. It's just we're not going to spend time on that. The goal is to try and build this. An x-intercept of negative 1 means that on top somewhere there should be an x plus 1, right? We're talking about where that thing becomes 0. Now, the last two things that remain, or last three things, are number 1, horizontal asymptote of y equals 0. Remember where this thing occurs. This occurs, and I don't have to distribute to show you this, but this occurs where you have a smaller degree on top than you do on bottom. On top I have, without full distribution, on top I do have x times x, which is x squared. On bottom I have x times x, which is x cubed. So I already naturally, through this setup, as long as I don't add other factors on top, I already have a y equals 0 horizontal asymptote going. So I don't have to do anything else to that. So I'm good there. I'm set there. But what remains here is looking at the y-intercept and this whole of 18/5. The y-intercept of 0, the y-intercept of negative 2 means we got to substitute 0 for x here. So let's see what happens when we substitute 0 for x in our current form of our equation. And it's in factored form. You don't get to plug in 0 and make things go away except for the x's. So when you plug in 0 for these, you're going to get 1 times negative 2 over 3 times negative 1 times negative 2. And that's going to give you negative 2 divided by positive 6. Negative 2 sixths, well, hold on a second. We needed negative 2 as our answer right here for the y. That means that, although there are no new x quantity factors I can add up here, where's our stretch factor? Where's that number? Let me find one. Where's like that 2 that's here, or that 4 that's here? Where's that other number that can come into play to make that a negative 6? What would make this thing, sorry, not negative 6, negative 2. What would make this thing a negative 2? Right now it's at negative 2, 6, right? It's like there's some stretch factor. I gotta multiply this thing by a. What does this a have to be so that this thing is negative 6? Well, we got the negative taken care of. We're good there. It looks like that it's dividing. Sorry, I keep saying negative 6. I mean negative 2. It looks like that this 6 is really the thing that's getting. What if I just multiply by 6? What if a was 6, right? Negative 2 times 6 would give you 12. And then a negative 12 divided by 6 is negative 2. If that a was a 6, that would do it. I mean, here's an algebra equation to solve it. Multiply both sides by 6, 5 by negative 2. You can solve it that way, but it's kind of just that, we need that number there. Sorry, it's got to kind of go here as well. So that a value needs to be a 6, right? If this was a 6, negative 2, 6 times 6 is indeed negative 2, right? Because those would cancel. So if this was a 6, you would be taking care of for that y-intercept. So we're squared away with that. Now let's check and see if that hole would work in here. And let's hope it would. Otherwise, we messed up. Otherwise, this problem is messed up. And then I blame myself because I made the problem. So if you plug in 2 into this is where you would have a canceled thing to play with it. If you plug 2 into here, you would get 6 times 2 plus 1 is 3. That's 18. Okay, so far so good. Over 2 plus 3 times 2 minus 1, right? So that's 5 times 1. So that's 18 over 5. Okay, so that comes out. So you plug it in, you get that. So yes, this is our function. Now, naturally, you tend to see these not in factored form, but expanded. So naturally, you'd see this like a big 6x squared, blah, blah, blah. But there's a factored form that you build from that, and that's just nice and fun. If anything, even if you're not tested on this kind of thing, right? If anything, you're making more sense of where you pull this information out from. The fact that you're dissecting and saying, where do those pieces fall? The 6 part's a little iffy as far as, what you would do with that. That's being more creative. But that's not out of the realm of a certain kind of problem that we've seen before when we tried to find stretch factors for quadratics and cubics and things like that. So there's that. All right, let's move forward to the back, if you will. And this is where we're going to be graphing. We got 4 things to graph, and then we got something involving a sign chart in factored form. We'll get to that. All right, the meat and potatoes of this thing. Graph the following rational functions. To do this, we want to try and get that information that we were getting before. Starts by factoring. So I'm going to factor the top here, and I get x minus 3 times x minus 1. On the bottom, there's a common factor of x to be left with x minus 2. So there are no holes, right? Holes, none. But there are vertical asymptotes, 2 in fact. 1 at x equals 0, and 1 at x equals 2. Horizontal, there's a tie with the 2's here, so the horizontal asymptote is going to be at y equals 1. And you know me with this. I like to do long division on this, and I'll do it over here. I like to do long division on these when I can. It can potentially give us more. I will do it if it's going to give us more information, and potentially ask, do we ever cross an asymptote again? Something like that. We do have to do long division if we have an oblique asymptote. X-intercepts are at 3 and 1, 3, 0, and 1, 0. And then y-intercept, we substitute 0 for x here, and we get undefined, and that makes sense. There is no y-intercept because 3 over 0. There was an x equals 0 vertical asymptote, so we don't expect to get it to cross the y-axis at all. So let's start constructing this graph here. I'm going to draw my vertical asymptotes here at x equals 0 and at x equals 2. We have x-intercepts at 1, 0 and 3, 0. We have a horizontal asymptote at y equals 1. Okay. I still want to do long division here, and the reason is because I want to know if we're ever crossing. We've seen moments where this thing could cross this asymptote right here and be on top, something like that. So I'm going to use long division to see if there's a time where the remainder, the numerator of the remainder gives us a 0 that we don't expect, or just anywhere. That can also help us with this part too. It totally can. So let's check it out. X squared minus 4x plus 3 divided by the way, when you do long division, you want to do it on a polynomial, so expand it out. But if you could simplify this thing, go ahead and use that. So you don't, if there were holes, if there were holes to take out, that you don't accidentally look at a hole and think that should be a filled-in point. X squared goes into x squared once. X squared times 1 is x squared. Negative 2 times 1, negative 2x times 1 is negative 2x. Subtract here, you get negative 2x. and then that plus 3. So this becomes, as a rewrite, 1 plus negative 2x plus 3. I don't like to write it that way. I'd rather factor out the negative, but that's okay. Over, and it's still x times x minus 2, and I leave that there in case we ever needed to play with sign charts. It's better to factor than not to. And check it out. The remainder to this guy here does have an x in it. That means we want to check its 0 out, because if the remainder here has a 0 numerator, that means there is a value where this turns into 0 here and y equals 1. There's somewhere where it crosses this asymptote. Let's figure out where it is. So where does negative 2x plus 3 equal 0? You subtract 3, you divide by negative 2, you get x equals 3 over 2. So we cross, that's 1.5. We cross the asymptote right here at 1.5, right there. That actually, I'll be honest, this tells me everything about the graph that I need to know. Remember, x-intercepts tell you not just where you cross, but it also tells you where you don't cross. So, and asymptote, where I cross the asymptote, this tells me where I cross. It also tells me where I don't cross it. So when we look at these regions to the left of this vertical asymptote, in between these two, and to the right, I see everything I need to know. My graph cannot be here, because otherwise it would have crossed an x-intercept, and it doesn't. So my graph needs to be up top. And no, this graph cannot have dipped down below right here and converged, because it would have crossed the asymptote somewhere. I would have gotten that information. So I know that my graph for sure comes from up here, not comes from, but, and goes that way. And I'm not getting specific points for you. I'm just getting the regions. I want to feel that out, because we know it doesn't cross the asymptote or any intercepts. In between, I got to get some curve thing here. Can it have come from the top to come back to here? No, because it would have hit on the asymptote. So it has to come from the bottom. It has to come from the bottom. It's going to hit that point here, and it needs to hit this asymptote here without hitting the x-intercept again. So it needs to finish upward. So this graph will indeed finish up here. It probably does more of a cubic thing like that. Probably curves off a little better like that, but that is the general nature of it. And then this one, again, doesn't hit the asymptote at all, but it does hit the x-intercept. So this one definitely needs to go in right here and then downward at this point. So that tells me everything I need to know. The long division was a godsend. It really did help me with that part. I didn't do anything else to it other than finding out where it crossed, and that's once again one of the benefits of long division. Now, I will say this part of the graph is probably really bad. It probably goes more like this to curve off, because it's probably more symmetric in line with that, but if not perfectly symmetrically in line with that. But that's okay. That's just the nature of the curve. You go to a graphing calculator and you say, yeah, I got where I was supposed to go with them, and that's it. All right, number 12. F of x equals x minus 4, already clearly factored on top. Over on bottom, we can factor this into x minus 4 times x minus 1. I mean, check this out right here. We got cancellation right there, so we're left with just 1 over x minus 1. Now, I'll tell you what. We've done these graphs in the past to the extent that I could do everything about this. This is my a over x minus h plus k kind of thing. We could do this straight up that way. But to keep it consistent with what we've been talking about, I think it's of our benefit to just continue on our path that we've done, which is we have a hole. We'd say this anyway, but we have a hole at x equals 4. We substitute 4 in for x in the simplified equation to see what the y value is that we jump over. So this is 1 over 4 minus 3, or 1 over 4 minus 1, which is 3. So 1 over 3, so 1/3. 4 comma 1/3. Vertical asymptote. There's still a vertical asymptote at x equals 1, the part that remains here, where we're still dividing by 0 in that instance. So x equals 1. There's a horizontal asymptote on this one because the numerator is smaller than the denominator, and that is at y equals 0. That means, we are not going to be doing long division on this one because we can't. This is in essence already a remainder as is. Heck, we're right here with it. This is already a remainder as is, but it's at y equals 0. Remember that a over x minus h plus k? Here's your h. Here's your k, right? There's the 0. So that's another hint toward that for you. X-intercept, we set, well, there is no x-intercept. 1 can't equal 0, right? It's about the numerator. We say set the numerator equal to 0. 1 can't equal 0. There is no x-intercept. Y-intercept, on the other hand, we can substitute 0. Let's do it in the simplified. Now let's just do it here. You get -4 over +4, and that's -1. So we get a y-intercept of 0, comma, -1. So let's go ahead and plot some features that we have there. We have a hole at 4, comma, +1/3. I believe it was a +1/3. A vertical asymptote at x equals 1. A horizontal asymptote at the x-axis, y equals 0. No x-intercepts and a y-intercept at 0, -1. Okay. You have everything on the graph that you can get out of it, that you want out of it. Sometimes we want to talk about sign charts and things like that. We don't need them. We don't need them because we know we don't ever cross this asymptote. There's nothing in long division to tell us that, since we can't use long division and there are no x-intercepts. So that just means we never cross it. So this point and this hole indicate for us that we'll be in this region, and there's nothing that you can do about that. Now, if we continued on a path that we used to do, if you remember this, you would take 1. It's kind of not a great number, but you take 1 and you would divide 1 by this, by 1 to get 1 right there, and by 2 to get 1/2, and by 3 to get, hey, 1/3, and like that, and divide by 1/2 to double it. So you would have found out that this would have been that graph like that anyway. So it's one of the old school ones, but kind of proposed in a different format like that. It's like, okay, I guess this problem was easier than the problem before it, one could argue. I almost don't remember creating this problem. I thought I would have had one of the more difficult variety, but that's okay. We can have it. I think it's a good way to take something you already know how to do and shape it toward some of the things that you're learning, talking about the whole intercepts and things like that. And we get a y equals 0 horizontal asymptote, because I don't think we get any more after this. Okay, number 13. Nothing to factor on top. And on bottom, it's a difference of 2 squares for x plus 3 and x minus 3. Nothing to cancel, so no holes. Vertical asymptotes, we have 2 of them at x equals negative and positive 3, where we would be dividing by 0. There's a horizontal asymptote. We got a tie for the leading degrees here, so it's negative 3 divided by 1. So you got a horizontal asymptote at y equals negative 3. If I see that correctly. X-intercept, we set the numerator equal to 0. When does negative 3x squared equal 0? Well, when x is 0. So 0, 0 is x-intercept, and guess what? That has to therefore be the y-intercept. Don't believe me? Plug 0 into, it's that point. There's nothing. That has to be the y-intercept. But plug 0 into here, you get 0 over -9, which is 0. So 0, 0 is the x-intercept and y-intercept together. We have vertical, horizontal asymptotes doing their thing right here and here and here. There's a little lovable symmetry to this. It looks, especially with that point there. Trying to think. Now, there's, long division can be had. I'm trying to decide if it's necessary. Yeah, I think it will be necessary here. There are some things that we can point to. The idea that we know it's not going to be coming from the top without hitting an intercept, so we know it's going to come from the bottom. The question does become, do we cross the asymptote, right? That's a question. On right here, do we cross the asymptote, right? We don't know. So we got to use long division on this thing here. I'm going to take negative 3x squared and divide it by x squared minus 9. X squared goes into negative 3x squared negative 3 times, where you get negative 3x squared plus 27. And subtract those things, and 0 minus 27 is negative 27. So your function is also rewritten as negative 3. One second. Negative 3 minus 27 over x squared minus 9, or x plus 3 times x minus 3. Again, I factor in case there's need to do something with that. Now, why does the remainder help me? And you could do sign chart. I haven't really spoken on sign charts with the remainder so much because we haven't had to use it. But what I have been speaking on is, could this numerator ever equal 0? Last time I spoke on it, I stated because there's an x up top, it can be. There's something to solve for. This one's just a constant, negative 27. That can't equal 0 on top. That means your remainder can't ever be 0. That means you're never going to hit y equals negative 3 because you're always adding or subtracting something to this, except at the vertical asymptotes. But you're always subtracting something or adding something here, right? Because you can't get a 0 up here. So what this is saying is you never touch this asymptote. It's never going to be touched. Now, what does that mean for the sake of what we're doing here? What does our graph look like? Well, if this is never touched and the intercepts are never touched here, that means that on the left and right corners of this thing, we for sure have our graph, doing this on this portion and doing this on this portion here, because we can't hit the asymptotes or intercepts. On this part, we have to somehow hit this point without hitting the asymptote. So we're not coming from the bottom and we're not going through the bottom. We're coming from the top and we're finishing at the top. And given the symmetry, I'm more than guessing that it's just hitting down like parabolically and coming back up like that. It's probably not going through right here and wanting to come. Well, actually, it can't. It can't, right? It can't have another intercept. So this thing absolutely is bottoming out, almost like a vertex. It's almost parabolic in nature, at that part right there and coming back up, right? So there it is. See, I like having that discussion. That's my own inner dialogue that I have when I'm talking about that problem. No sign chart needed. Once I know where I am or am not crossing asymptotes and x-intercepts, that really does help me come up with the rest of the problem. That long division really saves you when you're supposed to be using it. And we got to do it on number 14, because number 14, we have a larger degree on top than on bottom. We are going to have, folks, an oblique asymptote. So let's go ahead and configure it right now, shall we? We got to factor, the top. Do you see that top right there? It is a difference of 2 cubes. That's x cubed minus 1 cubed. So it turns into x minus 1 times x squared plus x times 1 plus 1 squared. X squared plus x plus 1, which, by the way, is not factorable, besides you testing that. That part's not going to be factorable. On the bottom, we have x minus 2 times x plus 1, I think. X minus 2 times x plus 1. So here's the factorization of that with nothing to cancel. No, you can't take the x plus 1s and cancel them. That's not how it works. Holes, none. The only problem with holes was the second one, I think. So no holes. Vertical asymptotes are at x equals 2 and x equals negative 1. As apparent there. Let's get rid of some of this fraction bar. Not fraction. What do you call it? Division bar. Horizontal asymptote. There is no horizontal asymptote. So there's an oblique asymptote because we do have a larger numerator degree than denominator. So long division would have been had anyway. Let's go ahead and get to it. Let's do x cubed minus 1 divided by x squared minus x minus 2. X squared goes into x cubed, x times. We've had ones with fractions where it would be like like a 1/2 and things like that. So just be careful with those ones as well, just to know that you can have them. But this one's not. So x squared times x is x cubed. Negative x times x is negative x squared. Now, that's not going to combine with the negative 1. And actually, neither is this. Negative 2 times x is negative 2x. So when you subtract, just be careful. This is, treat it, you're subtracting the negative. So it's going to be a positive x squared and a positive 2x and a negative 1. And then we are dividing here x squared minus x minus 2. X squared goes into x squared one time. And then you get x squared minus x minus 2 right there. And then subtract out, and then subtract the negative, you get 3x. And then subtract that negative, you get plus 1. So your quotient, so the function rewritten is, man, I really didn't give myself a lot of room here, which means I didn't give you a lot of room if you're using this PDF, is x plus 1 is the quotient, and then the remainder is 3x plus 1, all divided by x minus 2 times x plus 1. Again, factoring in case I need to use that. X minus 2 over x plus 1. So there's the rewrite of that. And I'm going to use that 3x plus 1 to talk about where we cross the asymptote, of course. But the x plus 1, this quotient right here, is your just like this was your horizontal asymptote right there, and just like this was your horizontal asymptote right there, this is your asymptote, but it's not horizontal, it's oblique. This x plus 1, this is y equals x plus 1. Y equals x plus 1. It is a slope-intercept form, y equals mx plus b, diagonal line with a slope of 1 and a y-intercept of 1. And we're going to be using that. Not only that, we got to find x-intercepts too, but not only that, we also got to find out where we're going to be crossing the asymptote, and I'll get to that. Let's talk about x-intercepts and y-intercept. X-intercepts at x equals 1. So 1 comma 0. And I mentioned this wasn't factorable. We talked about another one that wasn't factorable before. And if it's not factorable, then there's no... I mean, I need to go one step further. There are no real solutions to this one. Even if you try to solve using completing the square or quadratic formula, they are imaginary solutions, much like the x squared plus 16 was. Something you'd have to know off the bat, I suppose. But that's the point of this being a practice quiz exam, is it's harder than the normal things. We haven't seen a difference of 2 cubes in a while. This is just to show you that they can still occur. So it's not an x-intercept there because you can't get 0 up there. But it did lend its hand somewhere into this division. Somewhere it's going to take effect, and it probably has to do with crossing your slant asymptote here somewhere. Now your y-intercept, you set x equal to 0, and you get negative 1 over negative 2. So that's positive 1/2. So 0 comma positive 1/2. Okay, I have a lot of things in play. I'm going to go ahead and make this thing a graph. Let's get the vertical asymptotes in there at x equals 2 and x equals negative 1. Let's get the... I'm going to get the oblique in there in a second. I want to plot some of these other points. Let's get the x-intercept at 1 comma 0. The y-intercept at 0 comma 1/2. I'll see where this is going. Yeah, that's it. Okay, now let's do the oblique asymptote. So y equals x plus 1. So what that means is starting at y-intercept of 1, you're going to rise 1, run 1 like this over and over. Boom, boom, boom. So it's going to be a dotted line that's going across a diagonal like that, and that, I don't know if that calculation should move or not. Depends on where my points go. This helps you here to draw the dotted line later. So I'm doing light ones because I don't want to I don't want to think of them as points, right? I don't want to misconstrue them as points. Okay, that's all the information that we have now. There's one more bit of information that we can get, which is right here, the remainder. We might have to get more information. We'll see. But right here, 3x plus 1 can equal 0. This is where we touch, at the very least, where we touch the oblique asymptote. Subtract 1, divide by 3, you get x equals negative 1/3. So we hit the oblique, and that makes sense. So negative 1/3 is right here where we touch the oblique asymptote, about right there. So you can kind of see that progression of a curve that would be going through there and hitting the asymptote as it probably goes up. Talking about things we've talked about before. No other x-intercepts right here or right here, which is a big indicator of the fact that your curve is probably going through this part of the oblique asymptote. Not probably, it is. Not of the oblique asymptote, underneath, like it's with respect to it's underneath the oblique asymptote, so like that, approaching. Never crosses the oblique asymptote. We only have one place we know that it crosses, right there. Same goes for the top right? This thing is going to kind of trend closely to it like that because it never touches x-intercepts. Otherwise, it would have been on this side, right? It would have been, that was terrible. It would have been on this side and hidden x-intercept here, and same with this side, would have hidden x-intercept, but it never does. It never does. Now, in the middle, we talked about we do hit this x-intercept, we do hit this y-intercept, we hit this part of the asymptote. The only way to have that happen and not hit any other intercepts or asymptotes is starting from the top on the left and kind of doing that cubic thing going down, whoa, and curving off, sorry about that, going down at the bottom right like that, and that would be our graph there. All right, so that is the appearance of the graph. Again, letting the logic part take form. I didn't really have to do any sign charts on these. The idea of building a sign, and we're about to do one here, but the idea of building a sign chart is stating if you don't have information. If I didn't have this intercept right here, then maybe I'm lost as to Well, it's good. Well, if I didn't have an intercept, it would be a broken graph because I'd either have to come up through the asymptote again or something. You'd have to get more points. But if you're missing information, especially when you have a vertical asymptote on the y-axis and horizontal asymptote on the x-axis, then you're often missing those critical feature points unless you have a hole somewhere. So you really got to start doing sign charts to say, are we above or below? Because we just don't have enough information to tell us what's going on in the graph. So you start plugging in points for that. And that's what we're going to do here without graphing. Last problem. Given the factored function and sign chart, determine the signs for each interval on the domain. So this one's already factored for you just to kind of make things easier where you can just plug things in and play with signs. Now the values are as they are likely as a result of what would indicate zeros, holes, or asymptotes, vertical asymptotes. By zeros I mean x-intercepts. See this one? That's an x-intercept right there. That's an x-intercept. -2 is an x-intercept. You have a vertical asymptote here at x equals -4. It's undefined there. Sometimes you see people put a u there. And then at like 3, it's undefined there. And then at 0, it's also undefined. So you can see that at asymptotes, vertical asymptotes, and at intercepts, you can have these things. Now, there are things that are like squared and stuff, and that would definitely affect the graph, and you would be able to tell because it would affect the sign chart. And the sign chart's affected in a way that actually kind of helps us. There are so many different sign things here that we're going to have to plug in, but there are so many different factors to play with, but we can clean this up for ourselves a little bit. I'm going to start by plugging in, and the whole idea of a sign chart, guys, is plugging in a value that's to the left of -4, between -4 and -2, between -2 and 0, between 0 and 1, between 1 and 3, greater than 3. We're going to plug some values in and see what their sign is. Whatever their sign is, any other sign within that interval on the domain will be the same. It'll be the same sign. Because there's no critical feature, vertical asymptote, hole, x-intercept, or otherwise, that's stopping it from changing direction. That's going to allow it to change direction. It will stop it from doing it. By change direction, I mean on a graph, how do you go from positive to negative? You either have to cross the axis, go on an asymptote where you're on one side or the other side, or jump a hole. You can't just, well, you can, but not for rational functions. You can't just be right here and then boop, go on the other side. Even if you did, we would have recognized that as something on our sign chart. The whole point of the sign chart is these are critical values. So let's start plugging in values, and I want to show you how you don't have to do as much as you think you do. Let's try a number like -5. I'm going to test a little -5 right here and see what the sign is when I plug it in. So 4 is a positive number. -5 minus 1 leaves you with a negative. -5 plus 2 is negative, but you square it and it turns positive. Then down here, 3 is positive. Whoops. 3 is a 3. Down here, 3 is positive. -5. Okay, fine. I'll do 3 times -5. 3 times -5 is negative. -5 minus 3 is negative, but squared is positive. And then -5 plus 4 is negative. Cubed is negative. So you get positive times positive, which is negative, over negative times negative, which is positive, which is negative over positive is negative. So when you substitute -5 in here, you get a negative result. Okay, that was a lot of work there, right? Now we can reduce some of this work. Notice some things that I stated here. I stated 4 was positive. Well, yes. And it's going to stay positive. That's not going to change. Even the 3 right here is going to stay positive. Do the 4 and the 3, consider I'm not getting actual numbers out of here. Do the 4 and the 3 really matter? They're just going to give us a positive result from those two being there anyway, right? So do they really matter with what I'm trying to do with my test? No, they're just positive. They're just kind of being in the way. That -5 would still be a negative right there. It doesn't change having a 3. And you noticed even the things that I had that were negative to begin with, and when I squared them, they turned positive. Squaring something's going to make it turn positive as well. So these squares here, if those are just going to be positive and not affecting my sign difference, I don't need those either. So let's try these again with just using x minus 1 over x times x plus 4 cubed. Does cubing a value change its sign? No, a negative value cubed is still negative and a positive cubed is still positive. I'm not saying right here that this is the same graph as this. It's not even close. Not even close to the same graph. I'm saying that whatever I plug into here will get the same signs as what I get when I plug into here, because I eliminated all things that are just going to make a positive anyway. not make it positive, but keep the sign as whatever it'll be. So I get to do a lot less things. Let's try negative 5 again. Negative 5 minus 1. Negative divided by negative times negative 5 plus 4 is negative. Now you get negative over positive. So you can see I'm doing a lot less testing there. And I'm not going to write these each time. But you get a negative when I plug in negative 5. All right, let's go to between negative 4 and negative 2. Let's go to negative 3. So we get a negative on top divided by a negative times negative 3 plus 4 is positive. So negative over negative, which is positive. So we're going to get a positive when we substitute something like negative 3 or anything in between. Let's try between negative 2 and 0. Let's try negative 1. Negative 1 minus 1 is negative over a negative times positive. So this one is also positive right here. It looks like that this graph does something. It hits that x-intercept, and then it seems to bounce back up off that x-intercept. I think we've seen something like that before. So that's a positive result unless I mess something up. So that's going to be that. And again, that's kind of a result of having those squared things and doing whatever. It changes how things behave. Between 0 and 1, that's where you got to choose something like 1/2. A half. Whatever. You can choose whatever you want, but that's a good in between. A half minus 1 is negative. Right? And then 1/2 is positive, of course, and 1/2 is positive there. So negative over positive is negative. So we get a negative in that interval. Between 1 and 3, let's plug in 2. 2 minus 1 is positive. 2 is positive. 2 plus 4 is positive. Looks like everything here on out is just going to be positive, right? Even something greater than 3 minus 1 is still positive. So everything the rest of the way is also going to be positive. Now, I'm not planning on drawing the graph, so to speak, but this one does have a strange nature where you're used to seeing signs alternate all the time. You're used to going under and then coming from up top. And you probably see that pattern and say, does it always happen? Well, apparently not. Apparently not. You can have two positives in a row, two positives. And really, it has a lot more to do with these things being squared. In fact, that very much seems to matter. Notice how that's squared around the negative 2. It's like it bounces off of it. Right? And around the 3, it bounces off of it. So you can see where you can have things like that occur. It is very much possible, but that would be the final answer on the sign chart. Something that you might have to do time to time by plugging things in. Do it into the simplest factored form that you can. This wasn't simplified. This was making it simpler. Doing a lot less than I had to do up here. All right, guys, so that ought to do it for this one. Thank you so much for watching as we completed these doing rational function things. I wanted to go less than an hour. Looks like I didn't. But thank you so much for watching, guys. And I hope to see you in the next one. Take care.